today's session, we will be discussing about the reactions of supports. So different types of supports we have discussed in the previous session. This session we will be discussing about the reactions exerted by the supports on the members which are supported on them. So here we have discussed already about different types of supports, okay, and different types of loads and different types of beams also, okay. Simply supported beam, cantilever beam, and overhanging beams. These are statically determinate beams which we are going to deal with now. Only statically determinate beams. Continuous beams, propped cantilever, these are statically indeterminate. Okay, we will discuss them in due course, but now we restrict our discussion to statically determinate beams. So here, for equilibrium of any structure, the necessary conditions to be satisfied are, in case of planar force system, we have three equations of equilibrium: sigma fx0, sigma fy0, and sigma m0. Okay, so for a general case of force system, planar force system, these are the three conditions to be satisfied for equilibrium. Okay, so fx0, sigma here indicates the summation of forces. Okay, x indicates here the direction, x direction, y direction. Generally, we will take x direction horizontal and y direction vertical, and moment in xy plane or about z axis, which is perpendicular to the plane xy. You know, three mutually perpendicular directions, x, y, and z, isn't it? So this moment m is about z axis or in the plane xy. We can say both. Okay, that means we can say mxy is 0. That means the sum of the moments in xy plane is 0, or mz 0. That means sum of the moments about z axis. That is important. Okay. So here we simply write sigma m 0 about any point. Okay, A, B, C in the structure. Okay, if it is a beam, the sum of moments about any point, say A, B, or C. So the sum of the moments about any point must be 0. Algebraic sum here, it indicates algebraic sum. Algebraic sum means taking the direction into consideration. So for example here fx0 we call, that means the forces in x direction, along x direction. So if we take rightward forces positive, then we will take leftward forces negative. Okay, that is called the algebraic sum. That means taking direction into consideration. If we take rightward as positive, then exactly opposite direction as negative. Okay. Similarly, Fy0 indicates the sum of forces about along y direction 0. That means if you take upward forces positive, then opposite direction, forces in opposite direction means downward forces negative. Okay, sum of upward forces is equal to sum of downward forces. That is the meaning of this equation. Similarly, sum of rightward forces is equal to sum of leftward forces, or algebraic sum is 0. Similarly, sigma m0 means sum of anti-clockwise moments is equal to sum of clockwise moments. Okay, or algebraic sum of moments is 0. Anyway, we can say. Okay, so these are the three conditions to be satisfied for equilibrium. Okay, now coming to the reactions which are unknowns. The reactions are unknowns. So on a structure, we will be knowing the loads, external loads acting. For example, on a beam, we will come to know the forces acting. Okay, for example, some 2-point loads are there of magnitude 10 kilonewtons and 20 kilonewtons. Okay, so these are known. These forces are resisted by the reactions at the supports A and B. Okay, so the reactions at supports A and B are unknown and represented as RA and RB. Okay, now these unknown reactions can be found by using the equilibrium conditions sigma fx0, sigma fy0 and sigma m0. Okay, so finding out the reactions will be the very first step in analyzing of a beam. Okay, so in the analysis of beam, the finding out of reactions will be the first step in case of statically determinate structures we are talking about. Okay, so first we have to find out the reactions of supports. So now coming to the numerical examples, we can directly discuss some numerical examples. So how to apply the equations of equilibrium for finding out the reactions in different types of beams and for different loading conditions also. Okay, yeah, first consider the example one here. The beam AB of span 12 meters is hinged at A and is on rollers at B. Determine the reactions at A and B for the loading given in the figure. For the loading given in the figure. Okay. So you observe this beam which is hinged at A and supported at B on rollers. Okay. And the span of the beam is the distance between the supports. So here 4 plus 2 plus 4 plus 2. It is a total 12 meters is the span of the beam which is given here. Span is 12 meters. Okay. And how about the loading? There is a vertical load, point load of 10 kilonewtons acting at 4 meters from here. And two inclined loads. One is inclined at 30 degrees and at 6 meters from A, and the other one is 20 kilonewtons inclined at 45 degrees 2 meters from B. Okay, so how will you get the reactions now? So what are the reactions that you will have? At hinge there are inclined loads, so hinge support restrains both horizontal and vertical displacements. That's why it exerts vertical and horizontal reactions. Okay, it offers horizontal and vertical reactions. And coming to B, it restrains only vertical displacement. It is free to move horizontal direction in horizontal direction. So it offers only one reaction which is perpendicular to the support. Support is horizontal, so the reaction will be perpendicular to that. That means it is vertical. The support at B offers vertical reaction VB. So now we have three unknowns. Actually, these are components of the reaction RA, which is inclined at angle theta with horizontal. So the reaction at A, the resultant reaction at A is not vertical, it is inclined, which is the resultant of two components HA and VA. Okay, so we will find out first the components HA and VA, and then we will find out the resultant by using parallelogram law of forces. Okay, now how to find the reactions now? So first we, for this beam, first we will draw the free body diagram. What is free body diagram? We remove the supports first and replace them by the reactions. So at A there is a hinge, so we remove that and replace with reactions. Similarly at B we have a roller which offers vertical reaction. So we remove the supports first, all the supports, and we represent the forces, reactions offered by the supports. Now the loading as it is, we will show the given loading. One is inclined at 30, the other one is inclined at 45, 20, 15 and 10 in kilonewtons. Units are very important. The load is given in kilonewtons and the span is given in meters. Okay. So now this is the free body diagram for the given beam, the free body diagram. Okay. So first step we will draw the free body diagram. How to draw the free body diagram? By removing the supports and replacing them by the reactions offered, exerted at the support. Okay. So now we apply the conditions one by one. Sigma Fa Fx 0, that means sum of horizontal forces 0, and sigma Fy 0 and sigma m 0. Okay. So first we can apply sigma Ma 0. Sigma Ma 0. So we are taking moments about A. So what do you mean by moment? Moment means product of force and perpendicular distance, isn't it? So algebraic sum of the moments exerted by all the forces including reactions must be 0. Okay. And as we are taking moments about point A, the moment of the reactions VA and HA will be 0 because they are passing through the point. Okay. So you know that moment of a force is force multiplied by distance. Here the distance of VA from A is 0 because it is passing through the point. Similarly HA is also passing through the point. So they will have 0, they will produce 0 moment about A. That means we can eliminate these two from the equation now. Okay. So what will you have then? You will have the moment due to reaction VB and moment due to the external forces acting on the P. Okay. So VB into, what is the distance? 12, perpendicular distance. Okay. This is what type of moment it produces? It produces anti-clockwise moment, isn't it? It produces anti-clockwise moment about A. And coming to these loads, inclined loads, they will have the components along the axis of the beam and perpendicular to the axis of the beam. So we replace this by components 15 cos 30, which is acting along the beam, and 15 sin 30, which is perpendicular to the axis of the beam. Similarly here we replace this by its horizontal component 20 cos 45 and vertical component 20 sin 45. So we can replace a force by its components. Okay. It is clear. Now these horizontal components which are along the axis, they have their line of action passing through A. So the moment of this force and this force about A is 0 because they are passing through point A. Okay. So the vertical components only will produce moment about A. Okay, and what is the nature of movement produced by these forces? All are clockwise movements only. So what is the meaning of this sigma MA0? Sum of anti-clockwise movements is equal to sum of clockwise movements about A. So anti-clockwise movements are here due to reaction VB only, and clockwise movements are due to these forces, external forces. So what are the moments due to 10 kilonewton load? Is the moment 10 into perpendicular distance 4, 10 into 4 plus 15 sine 30 into perpendicular distance is 6 from here. So this is the vertical component and this is the horizontal component. So the distance of vertical component is 6 plus 20 sine 45 into, what is the distance? 10 meters. Okay. So here VB is only the unknown. So we get VB here from this equation. Okay. So once you get VB, then we apply the other condition, sigma Fy0. What is the value of VB? That you can calculate. Okay. Let us see the next slide. We have, this is the free body diagram. Just now we have drawn. Okay. The free body diagram in this case. So this is the free body diagram. So now the reaction at B is obtained from the equation. Sigma MA0 gives RB into 12. This is anti-clockwise, and these are clockwise moments. 10 into 4, 15 sine 30 into 6, 20 sine 45 into 10. So this gives the reaction at B as 18.8684. So next, we will apply the condition sigma V equal to 0. That means sum of the vertical forces is 0. So what are the vertical forces acting now? The component VA and VB. VB, RB, here RB we are calling it. So VA plus RB is, these two are upward and these are downward. So we have taken negative sum. Okay. So algebraic sum is 0. Or we can equate the sum of VA and RB to these forces. Anything is said. Okay. So this gives the reaction at A, VA, vertical reaction, as 12.7737 kilonewtons. Okay. And one more reaction, that is HA, which is obtained by applying the condition sigma H0. Sigma H ante sum of horizontal forces. Sigma Fx 0 or sigma H0. Both are the same. So what are the horizontal reactions, forces we have? The reaction at A and the components of forces 15 kilonewtons and 20 kilonewtons. 15 cos 30 and 20 cos 40. Okay. This gives the reaction HA, horizontal reaction HA, as 27.1325. So that is all. Okay. Now, the components HA and VA are replaced by the resultant reaction RA. Okay. So how will you get the resultant for rectangular components? Rectangular components. If it is A, B, then C is equal to square root of A square plus B square. When the components are at right angles, isn't it? So same thing we are using here. So the reaction RA is equal to square root of HA square plus VA square. And what is the inclination of RA with horizontal? Inclination of RA with horizontal. Here we have HA and VA, isn't it? So the reaction RA, which will be acting along the diagonal of this rectangle, and inclination is theta, and that inclination is given by this equation. Here alpha we are calling it, not theta. So alpha is tan inverse of, or tan alpha is VA by HA, isn't it? VA by HA. What is VA? 12.7737, and HA is 27.13. So HA is greater here. So the alpha will be less than 45. That is 25.2. If VA is greater than HA, then alpha will be greater than 45. And if VA and HA both are equal, then alpha will be 45. You know that, isn't it? So if VA and HA both are equal, then alpha will be 45. Because tan inverse V by H into 1. Tan inverse 1 is 40. If V is greater, then alpha will be greater than 45. If H is greater, then alpha is less than 45. In this case, H is greater than V. So alpha is less than 45. And alpha means the inclination of resultant with horizontal. Okay. So that is less than 45 degrees. So this is how we find the reactions at the supports. Okay. This is very important for any further analysis. Finding out the reactions will be the first step and important step also. Okay. Let us see some more examples. Second example, find the reactions at the supports A and B in the B, AB, which is shown in the figure. What do you observe here? This is also hinged at A and supported on rollers at B, but not on horizontal plane, on an inclined plane. The roller is resting on an inclined plane. You observe here. Okay. So what is the difference here? The reaction at A, at B will be now inclined to horizontal. Okay. The reaction at B will be perpendicular to the support. Okay. So the support is inclined at 30 degrees to horizontal. The reaction which is perpendicular to this will be inclined at 60 degrees to the horizontal. Okay. That is clear from this figure. And at A, as usual, we will have horizontal and vertical components of reaction. Understand? And what is the loading acting on the beam? There are 3-point loads, 60 kilonewtons, inclined at 60 degrees, 80 kilonewtons, inclined at 75 degrees, and one more load, 50 kilonewtons, is inclined at again 60 degrees. Okay. And the location of these forces is also given in the figure. And span of the beam is 6 meters. Span of the beam is 6 meters. Here, the reaction at B will be at right angles to the support, that is at 60 degrees to the horizontal. That is shown in the figure. Okay. Now we apply the equilibrium conditions. The free body diagram already we have seen. So sigma MA equal to 0. That is the first condition that we apply. So RB sin 60 into 6. RB sin 60 into 6. Okay. Then we resolve the force RB into two components. One is horizontal. Let us go to previous slide. we resolve this force into two components. First, RB cos 60 horizontal component and RB sin 60. So this horizontal component exerts zero moment because it passes through the point A, and RB sin 60, the vertical component, exerts a moment of RB sin 60 into 6 minus the this is RB sin 60 into 6 is anti-clockwise and the remaining are clockwise. So what are the remaining moments? The moments produced by the vertical components of the applied forces, and the horizontal components produce zero moment because they are along the axis of the beam. They have their line of action passing through A, so they produce zero moment. So the vertical component of 60 kilonewtons load is 60 sin 60 into distance is 1 minus 80 sin 75 into 3 minus 50 sin 60 into 5.5, that is equal to 0. So RB is equal to, because here RB is only the unknown, RB is equal to 100.4475 kilonewtons. Okay. Yeah. Second condition, sigma H is equal to 0. So that gives HA and the sum of rightward forces is equal to sum of leftward forces. So what are the rightward forces here? HA and component of 60. HA plus component of 60, which is 60 cos 60 minus 80 cos 75, and again plus all rightward forces are taken with positive sign and leftward forces are taken with negative sign. So RB cos 60 is leftwards, so it is taken with negative sign. Okay. So HA is now given from or obtained from this, substituting the value of RB, which is calculated in the previous step, okay, as 100.4475. So you will get the reaction HA, the component of horizontal component of the reaction at A. Next, the third condition, sigma V equal to 0. Sigma V equal to 0 or sigma Fy equal to 0. Both are same. Similarly, sigma H equal to 0 or sigma Fx equal to 0. So it means sum of horizontal forces. Sigma Fy 0 means sum of vertical forces. It is also written as sigma V equal to 0. So by taking upward forces positive, VA and RB sin 60, these two are positive, and downward forces negative. Okay, this gives the reaction VA as 85.5468. What is the difference between the previous problem and this problem is the roller at B is resting on horizontal plane in the previous example. Here it is inclined, the roller at B is resting on an inclined plane. Okay, that is the difference. That means the reaction at B is perpendicular to the support. At roller is perpendicular to the support on which the roller is resting. That you need to observe. Okay, the remaining is same. And next, the components are we find the resultant of these two components, HA and VA, as square root of HA square plus VA square. Okay, and its inclination. The inclination alpha. Here, tan inverse of VA is greater here. You observe VA is 85 point something and HA is 15.9. So VA is greater than HA. So the inclination alpha is greater than 40. You can observe that. Okay? This clear. Some of the examples on simply supported beams. Let us see one more example here. Yeah, here, what is the difference? This is also a simply supported beam with roller support at A and hinge support at B. What is the difference between the previous problems and this problem? So in this problem, we have distributed load along with concentrated loads. We have distributed load, uniformly distributed load, which is represented by as a rectangle here. You can see this. Okay. So the uniformly distributed load is represented by a rectangle like this, or it is also represented by this like this. Okay. This is also UDL with some intensity, and this is also UDL. Okay. So UDL is represented either by this way or this way. Both are uniformly distributed loads. Now, what is the intensity of loading for distributed load? 30 kilonewtons per meter. And what is the length of UDL? 4 meters. So the total load is obtained as the area of this rectangle. So the vertical side represents the intensity and horizontal side represents the length. Okay. So the total loading is WL. Small w, capital W is total load, which is given as small w. Small w means here the intensity of loading into length of loading. Okay. So total load for 1 meter the load is 30. So for 4 meters what will be the load? 30 into 4. So 30 into 4, that is 120 kilonewtons. Total load is 120 kilonewtons. Okay. And where will be the resultant of this UDL act? At the centroid. Centroid lies at midpoint of UD. The midpoint from one end, it lies at a distance of 4 by 2. Okay? 2 meters. 2 meters from either end. The centroid of rectangle lies at the midpoint, isn't it? So, while taking moments, we take the moment of the resultant. Because for point loads, we know the distance directly here. So 20 into 2. Because the load is acting at a point, the moment of that force can be directly obtained by multiplying with the distance. Whereas for distributed load, it is distributed over a considerable length. Okay. So while taking moment, how will you get the distance of resultant force? Resultant force acts at the midpoint, centroid. Okay. So that you must have an idea. Where will the centroid lie? For a UDL, for a rectangular load, for a triangular load, for a trapezoidal load. Okay. For a parabolic load. For all this, you must be knowing the centroids. Okay. Because the load will be concentrated at the centroid. Understand? So while taking moments, we take the moment of the total load W, which is obtained as product of small w into L, total load multiplied by the distance of the point of application, the resultant. Okay, where does the resultant act? It acts at the centroid of the rectangle, in this case of UDA. Okay, understand? That is only the difference. The remaining everything is same. That means we apply the same equations of equilibrium here also. Okay, yeah. Let us see. First, we'll apply the condition sigma mb equal to 0. Okay, we can apply both, either ma equal to 0, sigma ma equal to 0, or sigma mb equal to 0. Anything will be the same. Okay, so sigma mb equal to 0 gives Ra into distance 9 meters, that is the span, minus 20 into its distance. So same 30. Here you observe this. This is point load. 60 sine 45 is the component, vertical component, into perpendicular distance. 20 is point load into its perpendicular distance. Coming to this, 30 into 4 is the total load. Okay, and what is the distance? Centroidal distance from B. Let us go to previous slide. Yeah, we see the centroid here. It is acting at 2 meters from the end. Right? So total length is 4 meters. So it lies at midpoint. So from one end it is at 2 meters. So this is 2 plus 1 plus 2. What is this total distance from B? 2 plus 1 plus 2. It is 5 meters. So the distance of resultant load of this UDL. Okay. Then we can replace this UDL by resultant W. Okay, which is at a distance of 5 meters. So while taking moments about B, the distance of the total UDL W will be 5 meters. If you take the moments about A, then what will be the distance of this resultant load? Here 2 plus 2. 2 plus 2, only 4. 4 meters is the distance. Okay. So if you take moments about A, then distance of this resultant load will be 4 meters. From B, it is 5 meters. Okay. So 30 into 4 is total load into 5. That is the distance. Okay. So these are all anti-clockwise, and Ra into 9 is clockwise. Okay. That's why it is taken with positive, and these are all negative. Okay. So you get the reaction Ra. Now apply the second condition, sigma h equal to 0. So you have only one inclined load, 60, and its component, horizontal component, is 60 cos 45. So HB is this much, 42.4. Next, another third condition, sigma V equal to 0. So it gives the vertical reaction at B. Okay, by equating the sum of vertical forces to 0. Understand? And coming to the resultant reaction at B, again we'll use the same equation because these are rectangular components. The resultant is given by sigma square root of HB square plus VB square. Okay, so the resultant reaction is 100.20 and its inclination with horizontal is given by this. And in this case also VB is greater than or HB, so the inclination is greater than 45. The inclination is greater than 40. So these are all the examples on simply supported beams. Now let us see some examples on cantilever beam. Okay, you know what is cantilever beam? With one end fixed. Cantilever beam is one which is fixed at one end and free at the other. Here, if you observe, the fixed end is represented like this, isn't it? It is represented like this. So end A is fixed and end B is free, no support. So how will be the bending of this? So it bends like this. The slope at B is this one. At a tangent, slope at any point is the angle made by the tangent to the deflected curve with horizon. Okay. At this point, the slope is, if you draw the tangent to this curve, the angle made by that with horizontal is the slope. And slope at A will be 0 because the fixed support restrains rotation also. It will not allow rotation. Okay. So slope until nothing but rotation. Slope is nothing but rotation. So the rotation at A is 0. As the support restrains rotation, it offers moment. Some moment also is produced. Resisting moment, okay, is produced. In addition to the reactions, you will have a moment at the fixed support. Okay, and what are the loading we have? We have 3 point loads and 1 uniformly distributed load. Okay, so in case of cantilever, finding out the reactions is simple. Finding out the reactions is simple because you will get the vertical reaction directly by adding up all the forces, because sum of vertical forces is 0, isn't it? Sigma V equal to 0. That implies VA is equal to, which is upwards, VA equal to sum of all the loads. So we have 3 point loads, 20 plus 12 plus 10 plus the total UDA, 16 into 2, W into L, intensity multiplied by length. Okay, so this is capital W. Okay, total UDA. So what is the reaction now? 20 plus 42 plus 32. That is 70 kilonewtons. So that is the vertical reaction. And how about horizontal reaction? Sigma Fx or sigma H equal to 0. This gives HA equal to 0. Why? Because there is no horizontal force acting or inclined force acting. All are inclined at 90 degrees perpendicular to the axis. So they will have no component along the axis. Okay, no horizontal component of loading. That's why the reaction HA will be 0. And coming to moment MA, by applying, we replace this force, this support. Free body diagram we will draw first, isn't it? How will be the free body diagram? We replace this by the reactions and forces A, B. So now for equilibrium, sigma MA equal to 0. Let us suppose. Okay. So the moment produced by the support is MA and we are taking it in anti-clockwise direction. Okay. So sigma MA equal to 0, that gives sigma MA equal to 0 gives MA, which is anti-clockwise, minus, this is 16 into 2 total load and acts at a distance of 1 meter at the middle, isn't it? Total load acts at middle, which is at a distance of 1 meter. So minus 16 into 2 total load into centroidal distance 1. That is the moment due to UDL. And moments due to these point loads, 20 into 2 minus 12 into 3 minus 10 into 4, that is equal to 0. And algebraic sum of the moments about A is 0. So this gives directly the moment MA as 32 plus 40 plus 36 plus 40. So 80 plus 68, okay, 148 kilonewton meters. Units are important, kilonewton meters. That you can see in the next slide. So sigma H gives directly the horizontal reaction as 0, and sigma V gives the vertical reaction as 74, and sigma M equal to 0 gives MA, which is 148 kilonewton meters. That's all. So finding out reactions in case of cantilever is comparatively easy. Okay, this is another example in cantilever. Okay, so here end A is fixed and B is free. And what is the type of loading acting on this? We have one UDL 20 kilonewton per meter and 2 point loads 15 kilonewtons and 10 kilonewtons. And what is this? It is called couple. Okay, 30 kilonewton meters. It is called a couple acting. Couple under two equal and opposite forces. Okay, separated by a distance, small distance. They form a couple. Okay, if two equal and opposite forces are P separated by distance A, they produce a couple here. What is that couple? P into A. Okay, so that is given to be 30 kilonewton meters. It's a concentrated moment, we can say. Okay, and the span of the beam is 2 plus 1 plus 1 plus 1, that is 5 meters. Okay, so here the reactions can directly be calculated by applying the condition. Sigma V0 gives directly the reaction VA. Sigma H0 gives the horizontal reaction as 0, and sigma M equal to 0 gives the moment at A. Now, what is the moment at A? Point load UDL 20 into 2 into its distance is 1, and point load 15 into its distance 3, and point load 10 into its distance 5. And coming to this couple, that is already a moment, so we just take that value with the sign, because the moment is clockwise, that is taken with negative sign. Okay, understand? Here MA is anti-clockwise. MA is anti-clockwise, and we have two loads and a couple here, which is acting at some distance. It is immaterial. The distance of this couple is immaterial. We don't use this distance because it is already a moment. Just we will consider its sign and add it with proper sign. So it is being clockwise, it is taken with negative sign along with other moments. Okay, so this gives the moment at A as 165 kilonewton meters, and HA is 0. HA is 0. Okay, for now let me conclude this session. We will discuss some more examples in the next session.
Like, share and subscribe. Hit the bell icon for more updates.